Welcome back to Software Engineering 2FA3, Discrete Mathematics with Applications 2. My name is Bill Farmer, and we're going to continue with the topic of predicate logic. We're going to start by talking about variable binders. A variable binder is an operator that's applied to a variable and an expression that may contain occurrences of that variable. And the variable binder binds the occurrences of x in B to the collection of values that x ranges over. So variable binders are not like normal operators. It's not like a function that's applied to a set of arguments. It's a more complicated thing because we're thinking of the expression B in this case as an expression, and this expression involves occurrences of B, and the meaning of the whole binder depends on where these occurrences of B occur. Now there's various kinds of examples of variable binders in logic. We're going to be interested in this group two here: universal quantification and existential quantification. But there's other variable binders in logic. For instance, there's lambda expressions, or we can also say these are function abstraction. So something of this form, it denotes a function that maps x to the value of b at x. So that's function abstraction. Another example is definite description. Definite description maps, it denotes the value that uniquely satisfies B. So B is some statement about x, and this expression denotes the unique value that satisfies B. Now, of course, there may not be a unique value. In that case, the expression is normally undefined. And finally, there's indefinite description. Let me point out this. The symbol here is iota. In indefinite description, it's epsilon. And this denotes some value x that satisfies B. So the value of this will be some value that satisfies B, and if there is no value, it will be undefined. So as I said, the only binders we're really going to be interested in this topic are the universal quantification binder and existential quantification binder. And we've already seen that the universal quantification is a primitive variable binder in FOL. It's the only primitive variable binder. And we have a notational definition that we use to define the existential quantification binder. Now, variable binders occur all throughout mathematics. I've listed a whole bunch of examples here. When you have a variable binder, there is usually a variable which plays a role which is sometimes called dummy variable. Like here, with iterated addition, x is the dummy variable. X occurs presumably in B. The reason it's called a dummy variable is that we could replace x with another variable, let's say I, and replace all the x's in B with I, and we'd basically have the same expression, but the dummy variable has been changed. It means the same thing. Okay, so those are variable binders. Now, when you have variable binders, you have two kinds of variables. So let's say we have some signature sigma, and we have a term t and a formula A. We can ask the question, if we look at our term t or our formula A, what variables are free and what variables are bound? Or more precisely, what occurrences of a variable are free and what occurrences are bound? So a variable x that occurs in t is always free. In a term, all the variables that occur in t are free. Now, if we have a variable x in A, an occurrence of x in A, then can be either bound or free. It's going to be bound if it's inside, if the occurrence is inside of an expression on which the outside of it is a universal quantifier over x. So any occurrences of x and b are bound. And the occurrence of x is free if this is not the case. If x doesn't occur in any sub-expression of a that is bound by x using a universal quantification. So occurrences are either bound or free. Every occurrence of a variable is bound or free. And we say that a variable is bound in A if there is some bound occurrence of that variable. And likewise, we say it is free in A if there's some free occurrence of x in B. And we will say a term or a formula is open if there are variables that are free in it, and it's closed if there are no variables that are free in it. And a sentence is another name for a closed formula. Now, there's one more technical definition we need here. This is a definition that it's also sort of strange language, but this is what logicians like to use. We say T is free for x in A. T is free for x in A. If there's no occurrence of x in A, within A, there's no occurrence of x in A that is within a subformula of A of this form. So that means x occurs in a B where there's a binder in the outside, and y is free in T. So if a term is free for x in A, that means if I substitute T for the free occurrences of x in A, there will be no variable captures. So that's why this notion is important. If this is true, if we substitute T for the free occurrences of x in A, there will be no variable captures. Okay, so I have a question for you. In which of the following formulas of this signature to NAT is a variable x free? So I'll give you a moment to think about this. Okay, well, welcome back. In order for a variable to be free in an expression, that's a term or formula, the variable actually has to occur in the term or formula. So that rules out A right away because no variables occur in there. And B has variables, but x doesn't occur. So it rules out both of those. Now C has an occurrence of x. It is not bound by a quantifier, so this is a formula in which x is free. Now D has two occurrences of x, but these are bound occurrences. So this is not a formula in which x is free. And then E has three occurrences, and this one is bound because there's a quantifier here. This one is bound, and this one is free. So x does occur freely in E, but it also occurs bound in E. Okay, I have another question. I'll give you a moment to think about this. Okay, welcome back. Which of the following formulas of this signature is closed? Remember, a formula is closed, and another name for a closed formula is a sentence. A formula is closed if it has no free variables. If there's no occurrences of variables that are free. Well, we can rule out B because it contains no variables. We can rule out X. It has two variables, but they're both free. C has two variables, and there's three occurrences altogether. This is bound, and this is free, and this is bound. So there's a free variable, so this is not closed. D has just one variable. It is bound by this quantifier, so it's closed. And E has several variable occurrences. This is bound, this is bound, this is free. There's no quantifier outside that's binding Y. This is bound, This is bound. This one is bound by this quantifier, and this is bound. So there's one free occurrence, so this is not closed. Only D is closed. Okay, so one thing we could do is we can define the set of free variables of a term and the set of free variables of a formula. And we write this using f var of t, and we can write this as down here as f var of a, where t is a term, a is a formula. So I'm going to define f var of t using pattern matching. If you recall, in FOL there's only 3 patterns for terms: variables, constants, and function symbol applications. So if we have a variable, there's one free variable occurrence in that variable, and that's x itself. If we have a constant, there are no free variables. If we have a function symbol application, the set of free variables will be the set of free variables in T1, T2, T3, and so forth. So it's a union of those sets. Okay, so that's f var applied to T, f var applied to a formula. We're going to define this by pattern matching. There's 5 kinds of formulas, so we have 5 kinds of patterns. The free variables of an equality are going to be the free variables of the left-hand side union the free variables of the right-hand side. The free variables of a predicate application are going to be the free variables of all the arguments unioned together. This is very similar to the free variables of a function symbol application. The free variables of negation are just going to, negation of B are just going to be the free variables of B. The free variables of an implication, A implies B, will be the free variables of A, union the free variables of B. So far, everything is straightforward. Everything is straightforward because none of these forms involve binders, at least on the outside. They could have binders embedded in, let's say, B and A, for instance. But the last case, when we have a universal quantification, this is different because we have a binder. And the free variables of for all x a are going to be the free variables of a where we take away x. So x cannot be a free variable of this because x, this is a universal quantification and x is being bound. Okay, so we just define what the free variables are. In a similar way, we can define what the bound variables are. Now, the set of bound variables of a term is the empty set. When we had 3 ways of constructing terms, and these 3 ways of constructing terms don't involve any variable binders. So it's impossible for a term to have bound variables. This isn't always the case. If we go back up to these variable binders, if we had any of these 3 kinds of binders in our logic, then it would be possible for terms to have bound variables because the language would allow binders in terms. But in FOL, there are no binders in terms. Terms are built without binders. So to repeat what we had said before, a term has no bound variables. Of course, a formula can have bound variables because we have in FOL a binder for all. So the bound variables in an equality S equals T is going to be the empty set because terms don't contain bound variables. Likewise for a predicate application, the bound variables for not B are just going to be the bound variables of B, and the bound variables of A implies B are the bound variables of A union the bound variables of B. Now we get to the interesting case, the bound variables of a universal quantifier for all x A is going to be just the bound variables of A plus X. Whether X occurs in A or not, it does occur in the formula for all X A. So the bound variables of universal quantifier here is going to be the bound variables of A union X. Okay, so the next thing we want to talk about is substitution. So the idea of substitution is we have two kinds of substitution. Substitution of a term for the variable occurrences in another term, which we write like this. So we're taking this term and basically replacing all the occurrences of x with t. That's pretty straightforward. And we can define this precisely by pattern matching. And we have 4 patterns. You may wonder, well, we have just 3 kinds of terms. Why do we need 4 patterns? Well, we need a pattern where s is x and this is x, and we need a pattern where s is a variable that's not x. So when s is x, there's just one occurrence of x. We replace that with t. That's what our substitution says to do, so we'll get back t. If we have y, there's obviously no occurrences of x, so we just get back y. If we have a constant, again, it's obvious we have no occurrences of x, we get back c. If we have a function symbol application, then we're going to apply the substitution to every term. So it's going to be f applied to t1, to the substitution applied to t1, ... to substitution applied to tn, and so forth. Okay, so that's how substitution of a term for a variable in a term works. How does it work for substitution of a term for a variable in a formula work? So again, the idea is we're going to take all the free variables of A and we're going to replace them by t. And this is written, we write this in the same way we wrote it for terms. And we have 6 patterns. We have 2 patterns for universal quantification. So if we're doing a substitution of t for x in an equality, we get back the equality where we do our substitution of t for x in the left-hand side and t for x in the right-hand side. That's pretty straightforward. If we have a predicate symbol application, it works exactly the same as for a function symbol application. If we have the negation of A, then we basically just take the negation of the result of substituting t for x in A. And if we have an implication, we with an implication that's going to give us the implication that results from substituting t for x in A, the left-hand side, and then substituting t for x in B in the right-hand side. Now the interesting case again is when we have a universal quantification. If we have for all x A, and we're going to substitute t for x in that expression, notice this variable and this variable are the same, then this formula obviously can contain no free variables, no free occurrences of x. So we just get back the same formula. And if we have a variable y which is different than x, then we get back the result of taking the universal quantification of y, but we substitute t for x in A. Okay, so that's how substitution works. And here's a question for you. Which of the following substitutions is not correct? I'll give you a moment to think about this. Okay, well, welcome back. So we have this, let's start with A. We have this expression that has a free occurrence of x. And so if we apply our definition of substitution, we're going to replace that free occurrence of x with y, and we get this. That's completely straightforward. If we look at B, in B we have no free occurrences of x. These occurrences are both bound, so when we apply this substitution, we should get nothing. There should be no change, but look at what happened here. What happened here is that we have a y here. So actually this is an improper substitution. We're replacing a bound x with y. So this is an example that's not correct. These are correct. This is correct. If we look at this example, it's exactly the same, but this is correct. And remember, we're looking for not correct. This substitution was done correctly. B was not. And finally, we have D. And here, x is free. So we replace x with y. And we get this. The thing about D that is interesting is that we get a variable capture. X here is basically a free variable. Y here is a free variable, but the y here is bound. The way to think about it, we start with a free variable, we're replacing x with a free variable, and then it becomes bound. That is a variable capture. So the reason we are concerned about variable captures is that when a variable capture happens, it means that meaning is not often preserved. In other words, it's not sound reasoning. It is generally not sound reasoning to replace a free variable by a term in which that term has variables that get bound. Okay, well, we'll stop here, and next time we're going to start talking about the semantics of FOL. See you then.